Hey everybody, this is Miss Berry. In this video today we're going to go over section 7.3 and 7.4. So I'm going to go ahead and share my screen and we'll get started. All right, so section 7.3 is called using counting rules to find probabilities. I'm cutting a lot of this section out, but there are a couple of topics that I want to talk about. So first, let's talk about a couple of properties of probabilities. So some properties of probabilities. First of all, probabilities will always fall between 0 and 1. Inclusively, which means that probabilities are allowed to be equal to 0 and probabilities are allowed to be equal to 1. The closer a probability is to 1, the more likely that event will occur. So if you have a probability of, say, 0.8, then that is a probability that is higher or more likely than a probability of, say, 0.2. And then we have a couple of other things I want to note here. If you have a probability that's equal to 0, then that is called an impossible event. That means that event cannot and will not happen. Okay, so if a probability of some event is equal to 0, that means that it's an impossible event. And if you have a probability equal to 1, then that is called, that's an arrow, that is called a certain event. It is absolutely certain that that event will occur. All right, so we'll start off and we'll just look at a simple probability problem. All right, so it says, number 1, find the probability of choosing a letter other than the letter E from a bag that contains the 15 letters of the name Ernest Hemingway. Express your answer as a fraction in lowest terms or as a decimal rounded to the nearest millionth. Just for future reference, nearest millionth means 6 decimal places. All right, so suppose that you had this name, Ernest Hemingway, and maybe you took and you wrote each letter of that name on a slip of paper. Let me see if I can draw these boxes a little bit better. You drew each of the letters on a little slip of paper and you put them in a hat. Okay, so there's his first name, and then Hemingway only has one M. Well, I probably should have been spacing those out a little bit more. Let me try that again. Okay. So I'm just drawing all these little letters on a slip of paper, and I'm going to imagine that I'm putting them all in a hat or putting them in a bowl. I know this is taking me a long time, but I'm hoping that it's going to help you visualize what I'm doing here. Okay. All right, so I put all these letters in a bowl, and I'm going to draw out a letter. And I want to know, what is the probability of choosing a letter other than E. All right, so I'm going to cross out my E's. I don't want to consider them. Right, so there's an E, and there's an E. All right, so how many letters would be left over if I took out those 3 E's? That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so there are 13 letters other than E left, and they told us that there were 15 letters altogether. So there's my probability, 13 out of 15. That is a number that is between 0 and 1. You can make it into a decimal if you want to, but it's probably easier to type it in on the homework as a fraction. That's about 0.87 if you rounded. So that's pretty likely that you're going to choose a letter other than E. All right, so the most important topic that I wanted to talk about in this section is called the complement. So it's an idea called the complement of an event. So the complement of an event helps us to find outcomes that are in sample spaces that are sort of like the opposite of a certain event. So it says the complement of an event E, denoted by E with a little c in the exponent. Right, so it's an E, whatever the event name is, here they're calling it E, with a little c in the exponent, consists of all outcomes in the sample space that are not in event E. Right, and this is read as E complement. You may remember this word from back when we talked about sets. All right, so I wanted to give you just a simple example of a complement. So let's consider, or suppose you roll a die. So a standard die has 6 sides, and then we will consider the event E. I'm just going to call the event E here. Consider the event E of rolling an even number. All right, so our entire sample space here for rolling a die would be the numbers 1 to 6, because this is a 6-sided die. Those are the numbers we could roll. Out of that sample space, the even numbers would be 2, 4, and 6. So that's the outcomes that are in the event E of rolling an even number. Now the complement of E, so we're going to say find E complement, or the complement of E. So E complement, super easy to find. This is also a set. So you just take, it says it consists of all the outcomes in the sample space that are not in the event E. So you take all the outcomes that are in the event E, cross those out of your sample space, and the things that are left over are in the complement. So 1, 3, and 5. There you go. That's how you find the complement. Very easy. So it's sort of like the opposite of that event. All right, so let's look at an example from the homework. This is we're going to call this number 2. All right, so it says the following table lists the ages and number of players per age group that are on a soccer team. Let A be the event, or let A be the set of soccer players who are 10 years old. How many players are in the complement of A? All right, so we got this little table here. It says we have players that range in age from 8 to 11. We've got 6 players who are 8, 4 players who are 9, 6 players who are 10, and then 2 players who are 11. All right, so A is the event, the soccer players, or the set of soccer players who are 10 years old. So that's these people. So this is A. It says how many players are in the complement of A? All right, so A complement would be all the soccer players who are not 10 years old. So all of the soccer players on our team who are not 10. All right, so we just look at our little table. We say, okay, well, these people, they aren't 10, these people aren't 10, and these people aren't 10. So these three groups, this is all the people who are in A complement. So just add those up. 6 plus 4 is 10. 2 more would be 12. So there are, how many players are in the complement of A? There are 12 players in the complement of A. And that's it. All right, so let's move on to section 7.4. That was everything for 7.3. Section 7.4 is called Addition and Multiplication Rules for Probability. This section is much longer. There are lots of rules. So make sure you are getting these written down correctly. This is going to be something that you want to write on your index card for the next test. All right, so we're going to think about two types of events in this section. We're going to think about situations where we have, and let me change that color. So we're going to be thinking about situations where we have some event A and some event B. And we're going to be thinking about situations where we have an event A or an event B. So we're going to be thinking about probability questions that involve the words and or. All right, so let's start with our addition rule for probability, which is going to be those or problems. So these are the or problems. All right, so the addition rule for probability states the following. So again, I'm going to write up here, these are the or problems. So here's the addition rule for probability. I'm going to highlight the part that you should write down. Okay, so it says the probability of an event A happening or event B happening is probability of A or B is equal to probability of A plus the probability of B minus the probability of A and B. All right, so you have to subtract off what we call the intersection so that you don't count those numbers or those people or outcomes twice. So you subtract this part off so you're not counting people or outcomes twice. Okay. This is number 2. Go ahead and number that one. I'm going to come back and do this one about the word aardvark, but I want to do this one first. Let me put it on its own page because it's this page is kind of long. Okay. So I'm actually going to do this one first, and then I'll come back and do that one about the aardvark, the word aardvark. All right, so it says, use the following table to find the probability that a randomly chosen member of the Student Government Board is a senior or lives in off-campus housing. Express your answer as a fraction in lowest terms or a decimal rounded to the nearest millionth. All right, so we know that we're trying to find the probability that they are a senior or they live off campus. All right, so this is like our event A, and this is like our event B. All right, so using our addition rule from the last page, we have probability that a student is a senior or lives off campus is equal to probability that they are a senior plus the probability that they live off campus minus the probability that they're a senior and they live off campus. because we don't want to count those people twice. All right, so let's find these probabilities. All right, so we have this table here. It says we have freshmen, sophomores, seniors, freshmen, sophomores, juniors, seniors, and then graduate students. Let's find the total number of students altogether first, because we're going to need to know the total. Remember, probability is success over total. So let's add up these numbers. Let me get my document camera open here. Just going to switch to my regular calculator. All right, so just adding up my numbers in my table here. That went the wrong way. Okay. All right, so we have, just adding up the first column, 1 plus 3 plus 4 plus 3. All right, then in addition to that, I'm going to add in this column, 1 plus 3 plus 2. All right, so there's 17 people in the senior government board, or excuse me, the student government board. So total equals 17. Let's just write that in here. All right, so let's look at how many are seniors. All right, this is the senior row. So there's 3 that live on campus, 3 that live off campus. So there's 3 plus 3 is 6 seniors altogether. 6 out of the total, which was 17. Let's see how many people live off campus. Let's see, 1 freshman, 3 seniors, and 2 graduate students. So that's 1 plus 3 is 4, plus 2 more would be 6. All right, so again, that's another 6 out of 17. Subtract off the people who are seniors and live off campus. There were 3 out of 17 who were seniors and live off campus. All right, so get your calculator. Right, so we have 6 out of 17 plus 6 out of 17 minus 3 out of 17. You can use your little fraction button if you want to. All right, and there we go. It says round to the nearest millionth, which means 6 decimal places. You could also make this into a fraction if you wanted to. To make it into a fraction on this TI-36 X Pro, it's this button right here, which is right above enter. It's kind of hard to see because they're shiny, but this is the conversion button. Let's see if I can get the shadow to go away. No. Yeah, it's not going to focus on the, oh, kind of focused a little bit. Yeah, so that means conversion. So that's the conversion button. Goes fraction to decimal. All right, so if you want to, you can write that as 9/17, or you can do the decimal to 6 decimal places. I'm going to do 9/17 just because it's easier to write. There we go. Okay. Let's go back and do that aardvark question. You'll see why I wanted to do this one second, just a second. So it says, a single letter from the word aardvark is chosen. What is the probability of choosing a D or an R? All right, so probability of choosing a D or an R is equal to the probability of choosing a D plus the probability of choosing an R minus the probability that you choose a D and an R at the same time. All right, so we'll come back and talk about this in just a second, but let's see how many letters are in the word aardvark. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's 8 letters in total. All right, so D, there's 1 D in the word, so that's 1 out of 8, plus R, there are 2 R's in the word aardvark, so that's 2 out of 8. Minus, is there any way we could choose the letter D and R at the same time? No, right? Those 2 could not happen at the same time. We're going to talk about that actually in just a minute. But that's called being mutually exclusive. When two events cannot happen at the same time, that's called mutually exclusive. So this probability would be 0. It's impossible to choose those two at the same time. So we have 1 over 8 plus 2 over 8. These are really easy to add in your head. They have the same denominator. You can do it in your calculator if you want, but we have 1 plus 2 is 3. And we're allowed to do that because we have the same denominator. We have a common denominator. That's 3 over 8. And that's in simplest form, or lowest terms as they call it. Okay. So let's talk more about mutually exclusive events. So when two events are mutually exclusive, that means these events cannot occur at the same time. All right, so for example, you could not be 17 and 35 at the same time. So that would be mutually exclusive events. So we have, here's some more examples of mutually exclusive events. They list a bunch in the book. You cannot roll a 1 and a 6 on a single roll of a die. You could not buy a 15, well, actually, let's say this. You could not buy a red car, a solid red car, and a solid black car as your first vehicle. If you bought them both at the same time, one of them would not be your first vehicle. You would, at that point, have two vehicles. Okay. So just things that could not occur at the same time. But whenever we're talking about mutually exclusive events, we have a special addition rule for those. It's really simple. It's just built off of that last rule that we just saw. Right, and this is what it looks like. So this is the addition rule for mutually exclusive events. It says the probability of an event A happening or an event B happening when A and B have no outcomes in common. That's another definition of mutually exclusive. Another way to think about it is that they have no outcomes in common. It's just probability of A or B equals probability of A plus the probability of B. You don't have to worry about subtracting off their intersection because they have no outcomes in common. Right, so this is the addition rule when you are dealing with mutually exclusive events. All right, so let's look at another example. This is number 3, I think. The following table shows a breakdown of opinions for both faculty and students in a recent survey about the new restructuring of the campus to include an honors college. Find the probability that a randomly selected person is either neutral or opposed to the restructuring. Express your answer in lowest terms, as a fraction in lowest terms, or as a decimal rounded to the nearest millionth. All right, so I really like tables. Sorry, my USB drive came unplugged. I really like these problems with tables. Went there again. Fix that problem. All right, so I really like these questions that have tables. I think they're, easy to visualize. You'll definitely see one of these on the test. All right, so we're looking for the probability that someone is either neutral or opposed. So the probability that they are neutral or opposed. Oh, try that again. All right, so someone could not be neutral to the event and opposed to the event at the same time. So those are an example of mutually exclusive events. All right, so these are mutually exclusive because someone could not be both opposed to the restructuring and neutral about the restructuring at the same time. All right, so those are considered mutually exclusive. So we're using the addition rule for mutually exclusive events, which says that it's just probability that someone is neutral plus the probability that someone is opposed. All right, so this one is nice. It already has the tables all added up for us, or the columns and the rows all added up for us. So it says probability that someone is neutral. There was 65 out of the 209 in total that were neutral. Plus people that were opposed, it says there were 75 out of 209 who were opposed. All right, so let's add those up. $65 out of 209 plus 79 out of 209. I'm going to make that into a fraction. So it's 144 out of 209. 144 out of 209. All right, so next we're going to move on and talk about another probability rule. Oh, I'm sorry, no, we're doing another example. Sorry about that. This is number 4. I chose this one because they used the phrase mutually exclusive in it. So it says a bag of 11 marbles contains 7 marbles with red on them, 5 with blue on them, 6 with green on them, and then 4 that have red and green. What is the probability that a randomly chosen marble has either green or red on it? Note that these events are not mutually exclusive. So that means they could happen at the same time. You could have a marble that has green on it and red on it at the same time. And then same thing here, express your answers as a fraction, lowest terms, or as a decimal rounded to 6 decimal places. All right, so we're looking for the probability that a randomly chosen marble has green or red on it. All right, so it tells us here that they are not mutually exclusive. So we're going to use the probability rule for the original probability rule that we learned, which says probability of green or red is equal to the probability that you pull out a green marble plus the probability that you pull out a red marble minus the probability that you pull out a green and red marble. All right, so let's figure out what these probabilities are. We know that there are 11 marbles in total. Green marbles, it says there were 6 green marbles, so that's 6 out of 11. Plus, there were 7 red marbles, or 7 marbles with red on them, minus green and red. It said there were 4 out of 11 had green and red on them. All right, so again, this is pretty easy to do in your head. You're just going to add and subtract the numerators here. 6 plus 7 is 13. 13 minus 4 would be 9. But you can also do that on your calculators. Let me just show you. We'll also get 9 out of 11 if we do this on our calculator. Nine out of 11. So pretty high probability that we will get a marble that has either green or red on it. All right, next let's talk about the AND rule. The AND rule deals with independent and dependent events. So let me tell you the definition of what an independent event is and what a dependent event is. An independent event is an event where the result of one event does not influence the probability of the other. All right, so the result of one event does not influence the probability of the other. A dependent event is an event where the result of one event influences the probability of the other. So this one does influence the probability of the next. So these are pretty straightforward. Dependent events are going to, one of them will depend on the other. All right, so I took this problem off of the homework. Let's see, I think this is number 5. Okay, let's talk about independent and dependent events. So we're going to look at each one of these situations, and we're going to select the ones, or we'll, put a check mark on the ones that contain independent events. That's going to be events where the result of one event does not influence the probability of the other. All right, so it says 2 fair dice are rolled. The first die lands on 5, and the second die lands on 1. So does it matter, is the second die, is it going to depend on what your first die landed on? No, right? So whatever your second die lands on does not depend on what the first die was. So those are independent events. Next, we have pulling a blue marble from a jar and then pulling a second blue marble from a jar after replacing the first marble. All right, so since we replaced the first marble, that second time we pull a marble out of the jar is not going to be influenced by that first time we pulled a marble out of a jar. So these would also be independent events. If we had not replaced it, say we had just taken out that first blue marble, those would be dependent. But since we replaced the first marble, these are considered independent events. All right, the next one is smoking cigarettes and getting lung cancer. Do you think those are independent or dependent? That would definitely be dependent, right? Because smoking cigarettes can cause you to get lung cancer. So those would be dependent events because getting lung cancer could depend on smoking cigarettes, on whether or not you smoke cigarettes. All right, and then the last one is winning a marathon and winning the local lottery. Do those have any effect on one another? No. So those would also be independent. All right, so we're going to be looking at the AND problems here. We're looking at the probability of an event A and an event B. So let's look at our multiplication rule for independent events. So in order to use this rule, you need to know that your events are independent. Here's the rule. It says, this is one way that you can check and see if 2 events are independent. It says A and B are going to be independent events when the probability of event A happening and an event B happening is given by the probability of A and B is equal to the probability of A times the probability of B. All right, so if your events are independent, you can use this rule. Okay. So let's look at our first example. I'm just going to highlight again the part of the rule that you would want to write down on your little index card. Again, this is special for independent events. I think this is number 6. I like this problem. It says 3 cards are drawn with replacement from a standard deck of 52 cards. Find the probability that the first card will be a spade, the second card will be a black card, and the third card will be a 10. And then same as before, express your answers as a fraction in lowest terms. or as a decimal rounded to the nearest millionth. All right, so let's talk really quickly about that phrase with replacement. So we'll say, just as an aside, we'll talk about with replacement versus without replacement. All right, so again, when you do or when you complete two events with replacement, this is going to cause them to be independent events. If you complete two events without replacement, these are going to be dependent events. And these are pretty straightforward, the definition of with replacement, without replacement. Whenever you are picking outcomes with replacement, that means that your objects are placed back into consideration for the following choice. When you're choosing objects without replacement, then objects are not placed back into consideration for the following choice. And you can find that definition on page 316 of your textbook. All right, so let's find this probability. It says find the probability that the first card will be a spade, and the second card will be a black card, and the third card will be a 10. All right, so let's write that out. Probability of a spade and a black card, and then we choose a 10. So first we choose a spade, and then we choose a black card, and then we choose a 10. All right, so since we're choosing these cards with replacement, we know that these are going to be independent events. That tells us that we can go ahead and multiply the probabilities of these events. All right, and then just want to point out right here is where we see that keyword and. So that tells us we're using the multiplication rule. All right, so we're looking for the probability, that it's a spade. We're going to multiply that times the probability that it's a black card times the probability that the card is a 10. All right, so we talked about cards in class the other day. How many spades are there in a deck of cards? That's one of the suits. And we know that there's 13 of each suit. So we have 13 out of 52 that are spades. I won't put them, you don't have to put them in parentheses. Let me write it without parentheses. 13 out of 52 times black cards. We know that half of the deck is black and half of the deck is red. So that means half of the deck would be 26. So that's 26 cards out of 52 cards. And then there's a 10 card in each suit. So that means there's a 10 card that's a spade, 10 card of diamonds, a 10 of clubs, and a 10 of hearts. So that means there are 4 10s in the whole deck. All right, so let's multiply those probabilities. All right, so we have 13 out of 52 times 26 out of 52 times 4 out of 52. There we go. Let's see if we can make this into a fraction, just make it a little easier to write. And there we go, 1 out of 104. So that is the chances of us drawing a spade, and then drawing a black card, and then drawing a 10. There's 1 out of 104. Very small chance of that happening. Okay. Now let's talk about what do we do when we have to deal with dependent events. Events where one outcome will depend on the next, or excuse me, where one outcome depends on another outcome. So this is the definition of conditional probability. The key word to look for in these problems is the word given. So it says, or you can see it right here also. It says the conditional probability of an event B happening, given that event A is the probability of an event A, the event B, assuming that event A has already or will at some point occur. So you're looking at what's the probability that B happens given that A has already happened. This conditional probability is written as probability of B, then a long straight line, and then A. So probability of B given A. All right, so that long straight line means given. And it's read as the probability of B given A. All right, this is the rule for conditional probability. This is the formula. So it says probability of an event B given an event A is equal to the probability of an event B and A divided by the probability of A. So whatever the second letter or whatever the second piece is, that's what goes in the bottom. Now this top part, you can rewrite that as A and B instead of B and A. That's fine. So the letters here can be interchangeable. You can write them in whatever order you want. But whatever the letter is or whatever the event is after that long straight line, that goes in the denominator. All right, so let's look at a problem where we're dealing with conditional probability. Let's see. Last one was number 6. That's this number 7. Mr. DiNardo's literature class has 101 students classified by academic year and gender as illustrated in the following table. Mr. DiNardo randomly chooses one student to collect yesterday's work. What is the probability that he selects a male given that he randomly chooses from only the seniors? Express your answer as a fraction in lowest terms or as a decimal rounded to the nearest millionth. All right, so this is an example of dependent events because we are only looking at the seniors here. So that's going to have an effect on our choices. All right, so since we're only choosing from the seniors, that is going to affect, how many males that we have to choose from versus how many females we have to choose from. So we're looking for the probability that he selects a male given that he picks from only the seniors. All right, so he's choosing one student to collect the work. He's only going to choose from the seniors, and they want to know what's the probability that he chooses a male given that he's choosing from only the seniors. All right, so that's the probability that a student is a male and a senior divided by the probability that a student is a senior. Remember that second part, the part after the long straight line, goes in the denominator. All right, so male and senior. Male and senior, that was 18 out of the total 101 students. All right, so 18 out of the 101 students were males. Probability of senior, that is this whole row right here. So 18 plus 12, that is 30. So 30 out of the 101 students were seniors. All right, so now let's put this in our calculator. All right, so if you have one of the calculators that does not have a fraction button, let me show you how you're going to type this in. If you have a fraction button, just go ahead, hit your little fraction button, put your numerator up there, 18 out of 101, 30 out of 101. But let me show you how you would do this if you do not have a little fraction button. All right, so we would do parentheses, 18, sorry, let me focus this, 18 out of 101, close parentheses, divided by the denominator, put it in parentheses as well, 30 out of 101. All right, so that's how you would type it in if you do not have one of those fraction buttons. Right, so that's 0.6. You can make it into a fraction if you want. That would be 3 out of 5. All right, so you get the same thing over here. 3 out of 5. Oops. 3 out of 5. For a 0.6 chance that he chooses a male, given that he's only choosing from the seniors. All right. So that is everything for these two sections. Please let me know if you have any questions. And if you don't, I will see you in class next week. I'll talk to you then.